that A and curl of A are continuous on S. Those are mathematical, sometimes they may be mathematical terms, but the idea to remember is that if you have crossed a line integral of A dl, then you can always have on the right hand side, S is equals to curl of A with respect to ds, which is the cross surface area. Okay, now the open surface enclosed by the L. So this is an important formula, which is the one that is right there, that somehow you need to remember. It is the definition of the Stokes theorem. And again, the Stokes theorem is going to be well illustrated by the video that I have shared on the Google Classroom. So be sure to watch that video because it will show how those things come about. And the proof of the Stokes theorem is down there, which we are not going to bother ourselves with. And there's some example here, which we can look at very briefly. But before we look at this example, I would definitely take a pause, take a glass of water, and then if there is any question that someone might need to ask, they can ask now. While I take a glass of water. The example 3.8 ask us how do you find the curl of P. Curl of P is defined as, the first thing is to we are being asked, P is the one that is referred to as in example 3.6. Example 3.6 was where? Let's go for 3.6. Example 3.6. Example. Probably then I needed to lab some of this. Okay, I want to capture the 3.6, or we can do it very quickly. All right. Hope I can capture this. What happened? Salala, imeanza nini masaibu sasa hii? Imeanza masaibu. What is happening? I just want to do a screenshot. My goodness, they're not working together. It has refused. We don't want to waste your time. It has refused, so I think we can just capture x squared. We can try to remember this: x squared yz xz, xy squared, x squared yz xz. Yeah, so I won't write it here. P is equals to x squared yz ax plus yz az. I think that is how it was. Did I get it right? Someone confirm. So if that is our vector P, so we want to find the curl of P, you just have to put ax, ay, and az, and then d dx, d dy, x az. Ah, yeah, thank you for correction. Thank you for that correction. X, Z, A, Z. Thank you, Brian. And D, D, Z. Then the last row, we normally say A or P, PX. Of course, this is supposed to be PX, PY, and PZ. PY is actually 0. PX is x squared y, z. This is 0. This is x, z. And therefore, to find the first term, we just say is equals to ax into brackets. For those who are still struggling, I'm trying my best to show you how we do this. So we normally cancel this out. I never changed the color. What happened? Supposed to have changed the color. Oh yeah. See, cancel that out and cancel that out. Where A intersects, you cancel that row and the column. And then you say that this is going to be equal to what? This arrow minus this arrow. So this is plus, this is minus. You have d, dy, x, z minus d, dz of 0. And this, I think, will give us a 0. Yeah, this gives us a 0, and this gives us a 0, as you can see there. So that is the idea. I don't have to go through the entire process. So that is how we do it. And therefore, you're saying 0 minus 0 becomes a 0. The others are going to give you that, and the others will give you that. So the car of P is simply given by x squared y minus z in the AY direction minus x squared z along the z direction. And we move on. Of course, you can still do the example for along the idea is the same. You can do this for the cylindrical coordinate system and the spherical coordinate system. A bit demanding, but test tool should still give you the solution. So that is quite straightforward. We jump now to the other section that we need to deal with, which is the Laplacian of a scalar. Again, in the notes that I have shared, or in the videos that I've shared on Google Classroom, there are, I think, 2 videos. One introducing the concept of the Laplacian of a scalar. The other one is giving an example of Laplacian. So I know you'll be able to go through them, but on this case, I will still go through them in brief. And now say the following: that for practical reasons, it is expedient to introduce a single operator that is the composite of the gradient and divergence operators, which is known as the Laplacian operator. And by definition, the Laplacian of a scalar field V, written as nabla squared V. We are introducing this. Nabla is the same as del. I just remembered. And for sake of correction, in my previous lecture, I had referred to this symbol as phi, and this is not phi, it's actually called psi. So in case you watched a video or you were in that other class that I referred this one as phi, this actually is called psi. So that is for the sake of those who will watch the video later. So we can call this one nabla squared or del squared. This nabla squared is the one that illustrates the concept of Laplacian. And it is the divergence of the gradient of V. So if you have divergence of gradient of V, this is equals to nabla squared V. So that is the definition. Now, in Cartesian coordinates, of course, I've just defined it as such. And as such, that is the Laplacian of V. We know how we define the del. This is the del operator. And then this is the gradient. And if you remember about the dot product, this dot product, you see that the dot product, you multiply the coefficients of the unit vectors. So you multiply that with that, multiply that with that, and finally the other one, you multiply that with that. And what does that give you? It gives you, there's like double derivative, or double partial derivative, because we are saying d dx of d dx of v will simply become del squared v dx squared. This is I think double partial derivative, which is the second order partial derivative. So again, that is not new. In your mathematics, you must have met those concepts. And so that is what it means. It will just become del squared v dx squared, etc., etc. So that is the definition of the Laplacian operator, which is the Laplacian of a scalar in the Cartesian coordinate system. Okay, now, and you're saying that the Laplacian of a scalar field is another scalar field. So it's just important to know the outcome, what will come out of the Laplacian. Is that if you had a scalar, it will give you another scalar. Now, and the video that I've alluded to is actually talks about there is a concept of concavity. How concave is your curve? So that is the idea that you're going to see being introduced there. I don't want necessarily to go through them because it's the same thing like you can do by watching the video. But this is a point of inflection. This is a sine. If this is a sine wave, the point where it stops being, this is convex. If you remember the ideas of convex and concave. And I hope you do. I hope you have been introduced to those concepts. The point where my curve stops being concave to being convex or vice versa, this is normally called the point of inflection. Point of inflection. And therefore we are saying that the second order derivative tells you that this, if it is concave, it is positive. If it is convex, it is negative. So these are mathematical concepts that you will learn. But that is simply what the Laplacian operator tells you, that if you have a field which we are going to be dealing with sufficiently in electromagnetics, a field that is three-dimensional or three-dimension, then there are times when probably the field is positive or is convex. Then at some point it becomes concave. Therefore, we want to find out how much concavity or how much is our concave changing with the dimensions that we have. So I don't want to go into the details because that may lose some of you. All I'm saying is that the Laplacian operator defines for you the concavity of a field with the dimensions in two dimensions. So I have said that. So now beyond what we have said about the Laplacian, we have expressed it in the Cartesian coordinate system. Therefore, you can also express it in the cylindrical. And in the cylindrical, sometimes I just try to find a way I can remember these concepts. Remember the same way we did with the I can't remember whether it was divergence. I think it was with divergence. With divergence, we were introducing 1 over rho, and then we introduce rho inside, such that virtually this rho over rho would cancel out, and therefore there would be no much effect. But this is not how straightforwardly it comes. There is some derivation that allows you to show that. But for the sake of remembering, you can just say that you are introducing 1 over rho there, and it gets consumed, or it gets cancelled out inside when it is inside. Therefore, the other concept that he introduced is 1 over rho squared, for the sake of the one that we had. Remember, in the divergence, we had 1 over rho only, but now because we are doing it twice, then it is like you're multiplying with another 1 over rho, then it becomes 1 over rho squared. So that would be how I would try to remember those concepts if I was remembering them on my own. And lastly is the Laplacian of a scalar field in spherical coordinate system. Again, another complex one, but not too complex. Just introduce now 1 over rho squared there and 1 over rho squared there. So for the Laplacian, there is 1 over rho. And for the spherical, it is 1 over r squared. Again, 1 over r squared remains here for like it was here. So these are similar, except that you are introducing this sign that you are canceling out inside here. And this appear to cancel out. And lastly, the only thing that we are introducing that we never had is this term. So at the term of the phi component, introduce 1 over r squared sine squared theta. Again, I am saying that in ideal scenario, I should provide for you these formulas so that if you are doing the problem on your own, you would not require to remember this. You don't need to remember that, but the most important thing is that you know it exists. Like the way you know there is a pi, when you are finding the area of a circle, you normally say 2 pi r squared. So if you don't know pi, sometimes you can remember it is 22 over 7, but if you don't remember and you ask, you're going to be told. So the same way, if you want to find the Laplacian of an operator in the spherical, the Laplacian of a scalar field in the spherical coordinate system, then you definitely will need to know that there is this term called the Laplacian. And therefore, how you come up about it is something altogether. So the last but not least is that to mention that the Laplacian of a scalar field V, which is harmonic, is 0. This is what this equation says, that I mentioned that if this is a scalar component, this is the concave part, which is positive. This is the convex part, which is negative. If you have positive, negative, negative, positive, you add them up because it is a sum, you will get up with a 0. They would give you a 0. So it is very easy to remember that the Laplacian of a scalar field that is harmonic, such as sine or cosine, then it is easy to remember that that is how it comes about. Then there are some other properties that you might that might be worth remembering, like equation 364. And for me, I've actually not even remembered them. I think that should be sufficient for sufficient mention for the Laplacian. And then there's some examples here, which again, as long as you can have the formula, you can be able to find the Laplacian of this operator, of this scalar, which is defined in Cartesian coordinate system, following this example here, which again, I don't intend to go through because this is pure mathematics. So there's an example in cylindrical and spherical as well. So idea I've mentioned that you'd be provided with those formulas. The last concept I want us to talk about is the classification of vector fields. And it's more or less what I was saying, that if you know the direction and magnitude of a vector, then you can, from onset, be able to know if its divergence will be zero or non-zero. Like for instance, if you look at this figure 324, probably I should just zoom slightly so that you see. If you look at this one, you can simply see that at any point P, there is one vector that is getting, or one arrow that is getting in, and another one that is getting out. And therefore, the divergence of that vector is simply going to be zero. So if this is my vector A, the divergence of that vector is going to be zero, because it is not generating or absorbing any fields. They are just passing through. If this was some volume there, then all the arrows are getting in and getting out. Now looking at, but then if you look at the curl of A, you can see that if you determine or try to find out if this vector A is rotating, because that is what the curl tells you. If this vector is rotating, then its curl is not equal to zero. But if it is rotating, then the curl is zero. So what you can simply see from this is that this vector A is not rotating. Therefore, it has no rotating element, or it is not circulating. And for that reason, its curl is zero. So from our analysis of A, we can see that it is following this definition, that divergence of that vector is zero and curl of that vector is A. Now let's look at example B. What we can see is that example B, there is arrows are like emanating from a certain point at the center, and therefore very clearly from what we defined the divergence of a vector, we can simply say that there's something that is coming out of the volume. If this is my volume V, there is fields that are coming out of that volume, and therefore the divergence is not zero, but actually positive. Okay, divergence is positive, it is zero. It is not zero because there is some value because there are fields that are coming out of this volume from which the vector field is defined. Now, if you wanted to find its curl, the curl of this vector field, you can clearly see that if you wanted to go through this cross surface, you can see that there is no element or there is no arrow of this vector field A that is going around my sphere, my surface. And therefore, you can simply say that the curl of A, since there is no arrow or no element of that vector that is going along my loop or my service, then you can say that the car of that is 0. And that again guides us to agree that the car is 0, but the divergence is not 0. Now, I think following the same idea, we can go to the concept of the third field. So this field now, you can see that if you are to draw a sphere or a loop that is following the one that I have drawn, we can see that my vector field A is actually moving along it. There are some component of that vector A that is moving along that. And therefore, if you are to do curl of A, it will not be equal to 0. That is where we are here. What about its divergence? Is there any element that is coming out? If you are to find out, if you are to draw now that one, is there anything or any field or components of this field that are coming out? And what you actually see is that all of them are going around, but none of them are coming out, and therefore their divergence becomes 0. So that now marks part C. Last but not least is part D. And part D says there is some element of rotation. So you can see there is some element that if you are to resolve this, if you are to resolve each of these components along the direction of rotation, you can see that there's an element that is rotating. There is rotation or circulation. And also, if you are to resolve this one, they would have some element that is going outward, because that is what divergence means. There's some components of this vector that are leaving the volume, and therefore there is divergence. Then we are saying that divergence of A will not be equal to 0, and the curl of A, by the virtue of its rotation, is not equal to 0. So, having said that, there are just some additional components here that you would observe, which I think we have highlighted in that definition. And without really spending much more time than we have, I can say that the rest of the component about a conservativeness of the field and the rotation of the field, these are some things you can just briefly read on your own and understand. So that for me marks the end of this lecture. That is the end of this lecture, and the examples we have done plenty of examples. So on your own, you can capture the examples and try to do more. But that is the end of today's lecture. Before you go, I will definitely send you my pool. And I will also ask, respond to Mr. Mongi's question that is asking that do these have applications or they are only applied in exams? And I think the question is not very clear, but I would say that those concepts that we have gone through are very applicable in understanding the concepts of electromagnetics or engineering in general. Therefore, you definitely need to understand them. You may not, as we said in the beginning, you may not need to memorize all of them because they are not even possible to memorize. But understanding that they are there and how they are used, I think that is the most important. That is the most important concept. So please try to make sure that you understand what we're talking about. I can see that someone has raised their hand. Of course, you can ask the question, whoever is the hand, and we'll respond. We respond to your question when you have asked. So as soon as you finish responding to the pool, I will you can exit the meeting. And if you have any burning question, I will be glad to respond.